First of all, welcome back to today's MATH113, Section 7, Applications of Mathematics in Today's World. Now, today is day number 13 into semester week number 7. But unfortunately, when we look back to the schedule, according to our little arrangement, we have to do some catch-up because we spent time doing some practices. So if you look at the lesson plan on day number 9, that is in week number 5, if I remember correctly. Yeah. So this is lessons number, I guess lecture number 5, okay? So we need to help you to go through this lecture first, because if you look at the assignment questions, which is easier this week, which is going to be collected on October 25th, you have to know something in this section, okay? So we're going to soldier the lectures today, and then we go back to some important things that we need to do. But before that, let me just come to something much more important. Now, if we look at the calendar of this course, let's go back to week number 1. If you look at the calendar of this course, you will see that our midterm exam is scheduled in week number 9, okay? This is the scheduling of our midterm exam, which is in week number 9. But the second collections of homework will also be on week number 9. And that would not be very good in the context of normally, after you have submitted your work, I will give you suggested answers, okay? But if we set the midterm in this week, normally it's on October the 23rd, Friday. So I think it would not be very good in timing. So I have a suggestion. The suggestion is we will shift the midterm exam from week number 9 to week number 10, okay? We'll shift the midterm exam from week number 9 to week number 10. And I'm going to set this on October the 30th, okay, Friday, so that you will have all the suggested answers for the second set of homework for you to review in order to come to this midterm on October the 30th. So do you see what I'm trying to get to you? It's very important. My suggestion is to shift the midterm exam from week number 9 to week number 10. And it's going to be scheduled on October the 30th, the last day of this month, okay, in terms of the class, so that you will have the suggested answer released to you at least 1 week before the midterm exam for you to review, okay? That is very important. So you see that the midterm is going to be set on the very last day of this month. As far as the class arrangement is concerned, it will be set on October the 30th, okay? So do you see my point here? It's very important. So having said that, so you have to keep going with the second set of homework, which has already been given to you for 2 weeks, week number 5 and week number 6, okay? And I'm going to give you week number 7 in about 2 days' time, okay? So that you will have week number 7 homework set by the time we come back to class on Friday. So, and week number, this is October, week number 7, and you will have week number 8 here, okay? But you will not have week number 9, okay? So it's 5, 6, 7, 8. It's about 4 sets of practice questions. So if you understand that, that will be fine enough. So in order to help you with that, I have actually prepared several things today. But the first thing I just explained to you is we need to go back to day number 9 to let you learn from lecture number 5, okay? Because this is the missing lecture so far. If you trust me, you can actually see from here, I'm going to fast forward to week number 7 here. If you look at the Moodle environments arrangement, this is week number 6, okay? If you look at week number 6, day number 11, that is last week, we have just one day. At this point, last week, we did not review this according to our schedule. Instead, we used the time to show you 3 important practice questions on the product rule, the quotient rule, and the chain rule. So we will reserve that, and hopefully we can come back to this Friday. And again, when you look at day number 12, this is a holiday, basically it's a review of the first 4 lectures. And that is perfect for us. We've gone through this already. And so, if you're ready, if you go back to week number 7 again, principally speaking, this week is basically a review with. In the Moodle environment, I use Professor Leonard's material in order to make sure that you will have a much detailed review. So we are buying time by using the review time to go back to lecture number 5 now, okay, which is originally set on day number 9. And so if you're ready, so let's take a look at this. This is lecture number 5. So let's fast forward to lecture number 5. I got this from this week's before class activity, actually last week's before class activity. You have to go with me hand in hand because that is very important. So let's go for it. Let me just do this here. It's very important. This is week number 6. Let's go here. Yeah. I'm going to content learning. So we're going for lecture number 5, 6, and 7 is the target. So allow me to make sure everybody on the same page. If you have actually finished reviewing this lecture at home, consider this as a review. But for the majority of the class here today, it's important, okay? Let's go for it.
The following content is provided under a Creative Commons license.
Please make sure you take notes along the way, okay? We should have done this on day number 9, all right?
To make a donation or to give additional.
And this is an important step. That means to backtrack. Okay, I hope that you can accommodate this. Okay, here we go.
So we're ready to begin the 5th lecture. I'm glad to be back. Thank you for entertaining my colleague Ace Miller. So today we're going to continue where he started. Namely, what he talked about was the chain rule, which is probably the most powerful technique for extending the kinds of functions that you can differentiate. Now we're going to use the chain rule in some rather clever algebraic ways today. So
chain rules
the topic
in
for
some
today
algebraic
is
rings,
known as
okay?
implicit differentiation. So implicit differentiation is a technique that allows you to differentiate a lot of functions you didn't even know how to find before. And it's a technique, let's wait for a few people to sit down here. Physics, huh? Okay. Well, more physics. We'll take a break. You can get those after class. All right, so we're talking about implicit differentiation, and I'm going to illustrate it by several examples. So this is one of the most important and basic formulas that we've already learned part way, namely the derivative of x to a power is a times x to the a minus 1. Now, what we've done so far, what we've got so far is the exponents 0, plus or minus 1, plus or minus 2, etc. You did the positive integer powers in the first lecture, and then yesterday, Professor Miller told you about the negative powers. So what we're going to do right now, today, is we're going to consider the exponents which are rational numbers, ratios of integers. So A is m over n, m and n are integers. Alright, so that's our goal for right now, and we're going to use this method of implicit differentiation. In particular, it's important to realize that this covers the case m equals 1, and those are the nth roots. So when we take the 1 over n power, we're going to cover that right now, along with many other examples. Okay? So this is our first example. So how do we get started? Well, we just write down a formula for the function. The function is y is equal to x to the power m over n. That's what we're trying to deal with. And now there's really only 2 steps. The first step is to take this equation to the nth power. So write it as y to the n is equal to x to the n. All right, so that's just the same equation rewritten. And now, what we're going to do is we're going to differentiate. So we're going to apply dy dx to the equation. Now, why is it that we can apply it to the second equation, not the first equation? So maybe I should call these equations 1 and equation 2. The point is that we can apply it to equation 2. Now, the reason is that we don't know how to differentiate x to the m over n. That's something we just don't know yet. But we do know how to differentiate integer powers. Those are the things that we took care of before. So now we're in shape to be able to do the differentiation. So I'm going to write it out explicitly over here without carrying it out just yet. That's d by dx of y to the n is equal to d by dx of x to the n power. And now you see this expression here requires us to do something we couldn't do before yesterday. Namely, this y is a function of x. So we have to apply the chain rule here. So this is the same as, this is by the chain rule now, d by dy of y to the n times dy dx. And then on the right-hand side, we can just carry it out. We know the formula. It's m x to the n minus 1. All right, so this is our scheme. And now you'll see in a minute why we win with this. So first of all, there are 2 factors here. One of them is unknown. In fact, it's what we're looking for. But the other one is going to be a known quantity because we know how to differentiate y to the n with respect to y. That's the same formula, although the letter has been changed. And so this is the same as, I'll write it underneath here, n y to the n minus 1 dy dx is equal to n x to the n minus 1. Okay, now comes, if you like, the non-calculus part of the problem. Remember, the non-calculus part of the problem is always the messier part of the problem. So we want to figure out this formula. This formula, the answer over here, which maybe I'll put in a box now, has this expressed much more simply, only in terms of x. And what we have to do now is to solve for dy dx using algebra, and then solve it all the way in terms of x. So first of all, we solve for dy dx. So I do that by dividing the factor on the left-hand side. So I get here m x to the m minus 1 divided by n y to the n minus 1. And now I'm going to plug in. So I'll write this as m over n. This is x to the m minus 1 And now over here, I'm going to put in for y x to the m over n times n minus 1. Right? So now we're almost done, but unfortunately we have this mess of exponents that we have to work out. I'm going to write it one more time. So I already recognize the factor a out front. That's not going to be a problem for me, and that's what I'm aiming for here. But now I have to encode all of these powers, so let's just write it out. It's m minus 1, and then it's minus the quantity n minus 1 times m over n. All right, so that's the law of exponents applied to this ratio here. And then we'll do the arithmetic maybe just over here in the next board. So we have here m minus 1 minus n minus 1 m over n is equal to m minus 1. And if I multiply n by this, I get minus m. And then the second factor is a minus minus, that's a plus, and it's plus m over n. So altogether, the two m's cancel. I have here minus 1 plus m over n. And lo and behold, that's the same thing as a minus 1. Just what we want. All right, so this equals a x to the a minus 1.
See the interesting thing?
Again, just a bunch of arithmetic. From this point forward, from this substitution on, it's just the arithmetic of exponents. All right, so we've done our first example here, and I guess I want to give you a couple more examples, so let's just continue. The next example, I'll keep it relatively simple. So we have example 2, which is going to be the function x squared plus y squared is equal to 1. Well, that's not really a function. This, again, is a way of defining y as a function of x implicitly. There's the idea that I could solve for y if I wanted to. And indeed, let's do that. So if you solve for y here, what happens is you get y squared is equal to 1 minus x squared, and y is equal to plus or minus square root of 1 minus x squared. So this, if you like, is the implicit definition, and here is the explicit function y as a function of x. And now, just for my own convenience, I'm just going to take the positive branch, right? This is the function, let's just draw it right above here, right? It's really a circle in disguise, and I'm just going to take the top part of the circle. So we'll take that top hump. All right, so that means I'm erasing this minus sign. I'm just taking the positive branch. Just for my convenience, I could do it just as well with the negative branch. All right, so now I've taken the solution and I can differentiate this. So rather than using this dy by dx notation over here, I'm going to switch notations on over here because it's less writing. I'm going to write y prime and change notations. Okay, so I want to take the derivative of this. Well, this is a somewhat complicated function here. It's the square root of 1 minus x squared. And the right way always to look at functions like this is to rewrite them using the fractional power notation. All right? That's the first step in computing a derivative of a square root. And then the second step here is what? Somebody want to tell me? What? Chain rule. Yeah, that's good. Chain rule, that's it. So we have two things. We can start with one and then we do something else to it. So whenever we do two things to something, we need to apply the chain. So 1 minus x squared square root. All right, so how do we do that? Well, the first factor I claim is the derivative of this thing. So this is a half law to the minus 1/2. So I'm doing this by the sort of advanced method now because we've already graduated. You already did the chain rule last time. So what does this mean? This is an abbreviation for the derivative with respect to blah of blah to the 1/2, whatever it is. All right, so that's the first factor that we're going to use. Rather than actually write out a variable for it and pass through as I did previously with this y and x variable here, I'm just going to skip that step and I'm going to let you imagine it as being a placeholder for that variable. So this variable is now parenthesis. And then I have to multiply that by the rate of change of what's inside with respect to x, and that is going to be minus 2x. All right, the derivative of 1 minus x squared is minus 2x. And now again, we're glomming everything together here. We couldn't have done this example 2 before example 1 because we needed to know that the power rule worked not just for a integer, but also for a equals 1/2. We're using the case a equals 1/2 right here. It's 1/2 times, and this minus 1/2 here is a minus 1, right? So this is the case a equals 1/2, a minus 1 happens to be minus 1/2. Okay, so I'm putting all those things together, and within a week you have to be doing this very automatically. So we're going to do it at this speed now. You want to do it even faster, ultimately. Yes? The question is, could I have done it implicitly without the square roots? And the answer is yes, that's what I'm about to do. Okay? So this is an illustration of what's called the explicit solution. So this guy is what's called explicit. And I want to contrast it with the method that we're going to now use today. So it involves a lot of complications. It involves the chain rule, and as we'll see, it can get messier and messier. And then there's the implicit method, which I claim is easier. All right? So let's see what happens if you do it implicitly. The implicit method involves, instead of writing the function in this relatively complicated way with the square root, it involves leaving it alone. Don't do anything to it. In this previous case, we were left with something which was complicated, say x to the 1/3 or x to the 1/2 or something complicated. We had to simplify it. We had an equation 1 which was more complicated. We simplified it and then differentiated it. And so that was the simpler case. Well, here, the simplest thing for us, the simplest equation for us to differentiate is the one we started with. Because squares are practically the easiest things after first powers or maybe 0th powers to differentiate. So we're leaving it alone. This is the simplest possible form for it. And now we're going to differentiate. So what happens? So again, what's the method? Let me remind you. You're applying d by dx to the equation.